So vectors in a plane. First off, vectors are used to represent quantities such as force and velocity, both which involve magnitude, so that's size, the amount of force that you apply, and direction. You go in a particular, I go east, I go south, I push it left, I push it right, etc. So vectors are represented as line segments with an arrow. Now, in geometry, when we draw the ray like this, what does the arrow mean? It goes on forever. So in geometry, it means infinite, okay? This is not geometry, this is physics in this case. This does not imply it keeps going. This means direction. Two parts in the diagram has an initial point, a place where it begins, and a terminal point, a place where it ends. But like we said, the terminal point has an arrow, implying direction, not implying continuity. All right. All of these vectors right here would be called equivalent or congruent because, number one, they go in the same direction. And how do we know that? Because we can determine direction by slope. In other words, they have the same slope. But they also have the same magnitude. And how would I determine magnitude? Well, magnitude is just the distance between the 2 points. So how would I determine magnitude? Holy hashtag. Magnitude, that is a matter of distance. The distance formula. So, what we're going to look at today is a variation of slope. We're not actually going to calculate slope, but we're going to represent a vector in such a way that slope is just a quick ratio from there. And second, we're going to calculate the magnitude of the force, or the vector in this case. So, it's written in very, very funny terms, but it's not as complicated as you think. The most complex part about vectors is using a new symbol, a double bar and a double bar here. Up here, I do this bracket here and a bracket there. But really, it's like a point that is that represents slope. So, what is component form? Component form of the vector with an initial point P, P1, P2, and the terminal point Q, Q1, Q2, is the difference, effectively the difference of your x's, right? This here is delta x, the change in your x, and this one here is delta y. And when you subtract your x's and subtract your y's, you get a single number there for the x and a single number there for the y. Now remember that slope, we already know that slope is delta y over delta x, the change in x over the change, or change of y over the change of x. So when we put this in component form, we actually have the slope, just not written as a fraction, right? Because that's your change and that's your change. All we would have to do is write it as a fraction to see the actual slope. But when we put it in this form, it actually tells us direction, just not in that form. All right, the next part is how do we tell the magnitude, that is the length? Well, the magnitude, and we use this double line, the name of my vector, and double line. Generally, your vector is a boldface letter, so I tend to like thicken the V just a little bit on one of the sides, just so it has a bold face. All right, notice here, Q1 minus P1, Q1 minus P1, Q2 minus P2, Q2 minus P2. So what are we actually doing? We're just taking the vector component, squaring it, and this component and squaring it, and using that in Pythagorean theorem. So this is the distance formula, which is derived from Pythagorean theorem, and all we do is use the distance formula there. So we'll walk through some steps so we're not too complicated. Some definitions here. If the magnitude, so that's what the double bar means, is 1, then V is called a unit vector. And if the magnitude is 0, if and only if, V is the 0 vector 0. And of course, if it's 0 vector, that means no force is acting on whatever. So, okay. We already talked about two vectors being equal, but the key thing about them being equal is that when you find the vector in component form, and in component form, you get the same numbers. Like, this one gave me a 3, 4, and whoops. And this one gave me a 3, 4. Oh, great, they're the same. Because they had the exact same pieces. All right, so let's walk through this first example here. Example 1, let U be represented by the segment from 0, 0 to 1, 3. And let V be the segment or vector from 0, negative 1, and S is 1, 2. So our job is to show that they are the same. So for PQ, this is how we label PQ. We put PQ and we put a ray above it. Again, that just means vector. Now they actually told me that that has a different name besides PQ. They told me it has the letter U. So I'm actually going to say U here, and I like to thicken one of the legs just so it looks boldish. Now, all I do here is subtract the x's, 1 minus 0, and subtract the y's, 3 minus 0. Let's do that with red, 3 minus 0. And I put the brackets around it. And then the final result simplifies here. 2, 1, 3. The next one is vector RS. Again, they told us we're going to use the letter V. You don't have to write the RS down. You can just do V. And I just subtract the 1 minus the 0 and the 2 minus a negative 1. 2 minus a negative 1. Notice it's all around bracket. And I simplify that to get a 1 and a 3. So what do we notice? Because, in other words, when we take a vector like this and a vector that's placed in a different position, notice if I were able to, let's see, perfect. But if I have one vector, the black one and this blue one, and if I just take that vector and I put it on top of that vector, it should work perfect. If it were right on top of each other, then they would be the same vector. It's just they're in different places. In other words, I'm applying the same force in the same direction, just from a different place. So it's like you have the same gun and you shoot it from here, and then another gun, the same gun, and you shoot it from here. It's going to apply the same type of force to that bullet. I'm just having it from a different position. The magnitude. So we're going to find the magnitude, and how do we do that? Whoa, Nelly. Uh-oh. Okay, so how do we find the magnitude? Magnitude's as simple as this. Shh. To find the magnitude of V, we use the double bar. It's like absolute value, but different. Okay, and all we do is this. We take the 1, we square it. We take the 3, we square it, we add them together, take the square root. So all that simply becomes the square root of 10, and we could round that if we need to 3.1, but radical 10 is a fine answer there. Why, thank you. So vector operations are about taking a force, take for example this one here, and just moving it to the end point of the other one and just redrawing it. Tail to tip. And now what you get is a new vector that starts from this beginning to this end. Tail to tip. Right. So it's not so complicated because really all you're doing is combining the x values. All you're doing is combining the x values and combining the y values. That's it. It's not so complicated as think. And it turns out the same thing is true for subtraction. If you are subtracting, then you just subtract the x values, subtract the y values. Okay, so the next part is called scalar multiplication. And all we're saying here is that I have effectively a coefficient to my vector, which means I just send that number into both components. So if I'm going to double the size of my vector, that means I double the x and I double the y. That's it. And opposite simply means I want to move it in the opposite direction. So that means I don't change the size, so opposite doesn't change sides. It's like I'm shooting a gun, and all I do is turn around and shoot the opposite direction. Same force, different direction. In fact, opposite direction. So that just means take the opposite of the components. So not overly complicated. So what's this first one here? This first one says I'm going to take the opposite of 4 times v. So here's v. So all you have to do is quadruple each piece and take the opposite. So I get this equals -8 and +12. Why? Because -4 times 2 is -8. And -4 times -3 is +12. And that's it. We're done. So when we take a look at b and we say, oh, w minus 3v, what do? All we do is take this number, these numbers, and subtract the triple of v. So if you want to see the component that happens, I'm going to say, take the -2 from here, and I'm going to subtract triple of this 2. This -2 there, subtract triple of that one right there. So subtract triple of that -6. Repeat that process with this 5, and I subtract triple of this y component. So add 9. What? Add 9? Yeah, because I subtract the -3 there. So in the end here, I get -8, 14, and keep my funky little brackets around.